All right, so we are at the moment I'm sure you've all been waiting for, the final uh, calculation, the final video for doing truss calculations, and we are going to finally be able to determine the force within member BD. Okay, now we have already gone through, worked our way all the way around. As you'll probably notice on my drawing, I've replaced the member name, okay, so, member AD or member DE with the actual forces that we have found within them. And notice too that I have identified whether it is in tension or compression, okay? All right, now, if you have any questions, always refer back to any of these other videos, or you can always contact me. Now we have the option. We can either isolate joint B or we can isolate joint D. It does not matter. Either one of those will give us the result we're looking for there for member BD. Okay. So since we've kind of hung around on the perimeter, we'll go ahead and go through the process of solving this around joint D. Again, it really doesn't matter. Both of those members have, let's see here, joint D actually has 3 members on it and then 1 external force. Joint B has 4 members at that joint plus 1 external force. So I generally try to choose the one that has the least amount of variables associated with it. So we're going to isolate joint D. So again, like we did for all the others, we are going to redraw our free body diagram. Okay, now we are assuming that BD is in tension, so we're going to draw it that way. We know that DE is in compression, so it is going like that. We know that AD is also in compression, so it is pushing into the joint. Okay, and then we have our external force of 1,000 pounds. Okay. All right, we also have this internal angle here of 56.3. Okay, so this happens to be BD. This happens to be 1,378.9, and that's AD. This one happens to be DE, and it is 958.4. Okay, so we have the option. Again, we have the we need the X and the Y components for BD. So since we're assuming it's in tension, we're going to draw it like that. So this is BDY. Let me go ahead and kind of change this up. So I've got BDX right there and 56.3 degrees. Okay. All right. Here we have ADX and ADY. Okay. So nothing is different. We're going to go about this solving it the same way we've always done, which means starting our graph, so our X and our Y. So in the X direction, we have a 958.4 right here. That is pointing in that direction. Okay, we have BDX, which we believe is going that way. We have ADX, which is going this way. Okay. which we actually can easily solve for by using sine if we want, or cosine, either one. All right, and then in the y direction, we have 1,000 pounds. We have BDY, and then we have ADY. Okay, BDY we're assuming is going down. The 1,000 pounds is going down, and our ADY is moving up. Okay, so now it just depends which one we actually want to solve for. We have both of these we have as actually just as one unknown, because we know it. We can easily find ADX and we can easily find ADY. Okay, all right, so it just depends on which one we actually want to use. So why don't we, for sake, because we have this definite 1,000 pounds, these other values are somewhat rounded. This 1,000 we definitely know, so we're going to go ahead and solve for y. Okay, so some of the forces in the y direction, everything moving up, we have ADY, which is going up. That's the only one going up, so everything coming down, we have BDY plus 1,000. Okay, all right, so we've got that. Now, the question is, hopefully you guys remember by this point how to figure out the substitute for BDY. So it's just a matter of using SOHCAHTOA. BDY happens to be opposite of our internal angle. So we are just going to do that it is sine 56.3 equals BDY over BD. So again, multiply both sides by BD, and we get that BDY equals BD sine 56.3. So we can take that and substitute in. Okay. All right. Now, the other one is we have the ADY. Okay. ADY is just 1,378.9 sine 45. We've done this before, and what we should find is that it comes out to be 975. Okay, so let's see here. So if we do 1378.9 sine 45, comes out to 975. Okay. If you have any questions as to how we determine that, always refer back to one of the early ones, or just go ahead and email me. So I'm just going to go ahead. So that's ADY equals 975. And we're going to take that, plug it in there. So we have 975 equals BD sine 56.3 plus 1,000. Okay. Subtract 1,000 from each side. So minus 1,000 minus 1,000, and we get negative 25 equals BD sine 56.3. We divide by sine 56.3. Okay, and we get that BD equals negative, let's go ahead and take this, so 25 divided by sine 56.3, and I get a negative 30.049. Okay, so tell you what, we'll round that to negative 30.1. Okay, And as we know, it's not a negative value. It just means it is in compression. So I change that to 30.1 in compression. And then I can go ahead and I can update my drawing. And voila, we have found the forces within our entire system. Okay, now there's aspects to this that are a little bit easier because we had those 45-degree angles. Okay, now as you often know, one of the things that I like is to try to get you to identify shortcuts, be able to look at something and think critically and kind of come up with some basic conclusions to it. And this is no different. In fact, eventually you should be able to kind of look at this and say, oh yeah, I can kind of see that. So what I'm talking about right now is this idea. Notice that we have compression, compression, compression. Okay? Tension and tension. So if we look at it, you should be able to identify that, yeah, those should be in compression because of the fact that we have, it's got this support, we are pushing up here, and we have all these forces trying to pull down. So what's going to try to happen? This is going to try to push in as it tries to pull itself down. This, as these two members are trying to squeeze down, the only thing that's going to happen is this is pushing into here on both sides. So this member is also going to be squeezed in, compression. Okay, tension down here. This joint is trying to pull down. Well, if this joint tries to pull down, this member is going to try to lengthen. It's being pulled. Okay, tension. The interesting ones are these. This one's in tension and this one's in compression. Why is that? Well, if we notice, we have 250 pounds here, 500 here, 1,000 here. So we've got more force. If we were to divide this in half, we have more force on this side than this side. Okay? So what's going to happen is it's trying to pull itself in here. Well, if it's pulling down, kind of at this angle a little bit, this side is going to stretch. This side can't really go anywhere, so it's going to squeeze in that little bit. Okay? So that's why this one is in compression, that one is in tension. Okay? Now, what does all this actually matter? Well, when you are designing a bridge, a truss, whatever it happens to be, you can identify where we can use perhaps less material or a different type of material. This one is really small, 30 pounds only in here compared to 1,300, that kind of stuff, and it's in compression. So what type of beam might handle compression easier and is smaller and lighter weight, we can place it there, whereas this one might need a larger force, or sorry, larger member, and that kind of stuff. So that's how it really works. Okay. All right, so that is truss calculations, activity 2.1.6 in a nutshell. Remember, you're going to go ahead and take pictures of your engineering notebook as you've solved all this. And you're going to go ahead and submit it. You're going to utilize the skills that we just did here to complete activity 2.1.7, which I will be submitting a different version than what's on my PLTW. Okay, because I really don't like a couple of the problems in that one. All right. Thank you very much, and hopefully you guys are all master truss solvers.